Hi, welcome to Lesson 5D, Growth and Decay. We're going to be moving along and expanding on the information and the knowledge that you learned from Section 5C, sequences of, or geometric sequences, right? And so we're going to be looking at today our goal of learning how they apply to real-world applications. So basically, we know that there's some sort of a common ratio that would connect the subsequent terms in a geometric sequence. And so there can be growth or decay, so there could be an increase or a decrease in what we're looking for. And so there's different examples, of course, you can read here. And to begin with, we're going to be starting with some sort of initial condition, which occurs at time 0. And that initial condition would be like the initial value. And so at time 0, we've got what's called a zeroth term. So U1, or sorry, U0 is the initial amount, as we can see here and here. And that occurs when n equals 0. And when n equals 0, of course, r to the power n, well, this thing just equals 1. So then u to the 0 is u to the 0, or sorry, u sub 0, and that is therefore the initial value. Okay, r is the growth multiplier for each time period. N is, of course, the number of time periods, and u sub n is the amount, the final amount after n time periods. Okay, so let's take a look at an example to see how this all works. So the animal Eraticus is endangered. Since 2005, there's only been one colony remaining, and in 2005, the population was estimated to be 555 members. It's steadily decreasing by 4.5% per year. So we have to make sure that we read carefully what the instructions are telling us. So for part A, we want to estimate the population in the year 2020. Okay, so if we start off with the formula, u sub n equals u sub 0, r to the power n, well, we need to know what that the ratio is, the growth multiplier. And in this time, because it's decreasing, is going to be not a growth, but it'll be more of a decay. So usually what happens is we'll have that r is going to equal 1 plus I, or I mean, that's in terms of interest, but that's the increase or decrease. Well, because we're decreasing in this case, it's going to be 1 plus, it's going to be negative 4.5%. And the 4.5%, we have to write that as a decimal. Okay, so as you know, 4.5% equals 4.5 per 100. And then when you divide that, you get 0.045, and that is our decimal value that we're going to be using. So it's going to be negative 0.045 for the rate, for the growth rate. And when you subtract that from 1, you get 0.955. So that's going to be our rate of change, or not a rate of change, but that's our factor. And so estimate the population in the year 2020. Well, initially, we looked at it in 2005, and so 2020 is the next time we're going to look at it, which means that the number of years that have elapsed would be 15. So we're going to be looking at the 15th term, and u sub 0 is 555, and the rate is going to be 0.955 to the exponent 15. Okay, and so I'm going to show you the calculator. So Wabbit Emu is what I use, and I'm going to have to stop sharing this so that I can share the calculator. There we go. And so we turn this on, and is it on yet? I don't see it on. There it is. Okay. So we're going to be substituting in, well, we're going to be putting in 555 multiplied by, and I'll put this in brackets just so I can keep things straight. 0.955 to the exponent 15. And then I'll hit the right arrow to bring it back down onto the main line, and I'll close that bracket, hit enter, and so we're going to get 278.19. If I can remember that as I head back to the smartboard. And so that's 278.19. So approximately equal to 278 members of that population. Okay, so that's fairly straightforward. Now we're going to find out, well, in what year do we expect the population to have declined to 50? And of course, that 50 is our final amount. That's our U sub n. So we don't know the value of n at this time, so we're going to substitute into the equation or into the formula 50 as U sub n. U sub 0 is still 555. We know the rate of growth, well, in this case, decay is 0.955, but we don't know how many years that's going to take. So we'll divide both sides by 555 because we need to know, we need to isolate for the exponent. So we'll leave that as that for now. And so that value, I'll head back over to the calculator for a second. And so 50 divided by 555 is 0.09009000901. I'm sure it would just continue on in that pattern. So I'll have to jot that down. And so I head back over to the smartboard. And so that is 0.090090009, et cetera, et cetera. I don't want to go on ad nauseum with this. That's 0.955 to the power n. So now this is in exponential form here, but in order to solve for this exponent, remember we get to use logarithms now, which is great fun. So I'll rearrange this into logarithmic form. So the logarithm, and 0.955 is the base. So it's going to go down here in the base. And we need to, this is your final result here, 0.090090009. And then that equals the exponent. Remember that logarithms are exponents, and therefore the logarithm equals the exponent, and the exponent is n. Therefore, we set it up in this way. When you're in the process of doing the calculations, it's probably a good idea to carry as many decimal places as possible so that you maintain the best accuracy as possible. And then we'll round to 3 significant figures at the very end. Okay, so I'll then show the calculator calculation for this. So this is eventually going to equal n. And so when we go to the calculator, so there's a bunch of different ways to calculate things on the calculator, but to find the logarithm, you go to math, and then you can arrow down past fraction decimals, cubes, cube roots, et cetera, derivatives, integrations, summations, and all that. Oh, and there's log base right there. So that's A. So you can go math and then scroll down to A, or, and I'll just quit this for now. I'll show you, you can, and see there's that green A just above the H in math. And then there's a B above apps. There's a C above program, etc. D above this x to the -1. If you hit alpha, that will then indicate the letter that of the button you push. So that's going to be A, alpha apps is B, etc. So if I go math, and then remember log base was A, I go alpha math, and I get right to that. Okay, so the log base, and the base was 0.955, and then I go up, or I go over into the bracket, and then substituting in 0.09009,009. Okay, and I'll go outside the bracket, press enter, and we get 52.275, I suppose, 52.275. All right, so I'll go back to the smartboard, and N is 52.275, or approximately equal to 52 years. It's probably, well, it's obviously going to be a little bit more than that, because to get down to 50 members, it has to go past 52 years, but it'll be probably in the 53rd year. So it's around 52 years kind of thing. So that is how we find out this exponent, how many years it'll take that initial population of 555 erraticae to dwindle down to 50. All right, let's move on to the next page. And now we've got a herd of deer. And there's 32 to begin with, and they're left unchecked in a new sanctuary. And of course, there's going to be an increase this time by 18%. So the 18%, as you can probably figure out pretty quickly, we use a decimal as 0.18. And we want to estimate the size of the herd after 5 years. So part 1, U sub 5 is our 32 initial value, and it's 1.18 because it's always 1 plus the increase, because the 1 takes care of takes into account the initial value of the herd of 32, and N is going to be 5. So we just have to substitute that into the calculator, and I will save you my hassles of going back and forth between the smartboard and the calculator. And just trust me when I substitute all this into the calculator, and I get 73.208. So it's going to be approximately 73 deer after 5 years. And then after, in part 2, part 2, we're going to be looking at after 10 years. So U sub 10 is 32, again, times 1.18 to the exponent 10. And then when I do this calculation, I end up getting 167.483. Now, we can't really go up, we can't round up to the nearest whole deer. We have to round down to the nearest whole deer. And so that's going to be approximately equal to 167 deer. Even if this were 167.7 or 167.8 deer, we'd have to round down, because you can't just magically round up a whole deer. You can't just formulate more matter out of something that's not there. So I always suggest you round down. Maybe the textbook answers might round up, but I'm not a big fan of that because it's not accurate. Now we go to part B, and we want to see how long it'll take the herd size to reach 5,000. Well, we're going to do the same thing as we did in the last example with the poor herd of the erraticae. And so the final amount that we're looking at is 5,000, and the initial amount was 32. And again, it's 1.18 as the growth factor, and we don't know how many years that's going to be. So we'll divide both sides by 32. And we got 1.18 to the power n. And so this is going to end up being 156.25. And then we'll put it in, so this is an exponential form, we'll put it into logarithmic form, and we know that 1.18 is the base. And the final result is 156.25. And then this will indicate the final number of years for that herd of 32 to grow to a herd of 5,000, and it ends up being 30.52, and so that's approximately, if we go to half years, perhaps 30.5 years in order to reach that goal. Okay, so that's about it for lesson 5D. Here's a little bit of work for you to practice on. Thanks for watching, and we'll see you in class.